And so James is today's speaker. So he is now associate professor at Shanghai Jiao Tong University, math department. And yeah, he got his PhD from Florida State University, and after his PhD, he did his post doctoral research in at here HKU, also in math department. And during his postdoc, he worked on geometry of string theory. But recently, he started shifting to work on information theory. Today he will talk about quantum states over time, which is very interesting. And yeah, I will give time to you.
Okay. So thank you very much for the introduction. It's good to be back here in Hong Kong. Okay. So I will start out with some motivation. Okay. First, I don't know if we have. Let me see. Do we have? Can those of you online hear me okay? Yes? Okay. Okay, so to start out with motivation, the problem that got me sort of started on quantum states over time is the following. So in quantum information theory, right, we have the quantum joint entropy, the quantum conditional entropy, and the quantum mutual information of a bipartite quantum state, rho AB, are given by the following formulas. So the quantum joint entropy is given by S of A comma B equals S of rho AB, where rho AB is a joint state corresponding to two systems, quantum systems A and B. Okay, where S is the von Neumann entropy of the joint state rho AB. The quantum conditional entropy is given by H of B given A, which is the joint entropy minus the von Neumann entropy of rho A, where rho A is the reduced density matrix associated with rho AB, corresponding to partial tracing out the B system. And the quantum mutual information, there are various ways to write it, as well as the quantum conditional entropy. But the shortest way to write it, which could fit on my slide, which is the von Neumann entropy of rho B, which is the reduced density matrix of rho AB, corresponding to tracing out the A subsystem, okay, minus the conditional entropy. Okay. So note that in this case, rho A and rho B are space-like separated states, or states associated with space-like separated regions A and B. Okay, so in other words, there's no dynamics involved in this formulation of these information measures, right? So for example, rho AB is just a state at a single time, and the states rho A and rho B are also just states at a single time, space-like separated states at a single time. So what led me to states over time was to consider, are there, the question of whether or not there are dynamical analogs of the quantum joint entropy, the quantum conditional entropy, and the quantum mutual information, right? So for example, what if rho A and rho B are time-like separated? So what if, in other words, what if they're the input and output states of a quantum channel E, right? Are there also, dynamical formulations of, these quantum information measures in such a case when rho A and rho B are time-like separated? Okay. Now, to provide an answer to this question, I'll look at the classical case where the answer is in some sense trivial. And then what I'm going to do is introduce a mathematical formalism which treats the classical case and the quantum case with the same mathematical formalism. So therefore, I can talk about classical channels, I can talk about quantum channels, or hybrid classical quantum channels in the same mathematical formalism. So what I will do is first talk about the answer in the classical case, and then reformulate that answer in this mathematical formalism that treats both the quantum case and the classical case on the same footing. Okay, so for that, let's first look at the classical solution. Okay, so with the classical solution, we start out with a classical channel F, okay, going from X to Y. So X and Y are finite sets corresponding to the inputs and outputs of some classical communication channel. Okay, and mathematically, this amounts to associating conditional probabilities F sub Yx, okay, where F sub Yx is the probability of the output of the channel Y given the input X, okay? And if P is an initial state on X, by an initial state, I just mean a probability distribution on the inputs X of the channel, okay? Then there's an associated joint state on X cross Y and the Cartesian product of the two sets, okay? And everybody knows what this joint state is, okay? But I'm kind of using this quantum language to talk about this as we want to, eventually view the classical channels and quantum channels on the same footing, okay? And this joint state is a probability distribution on X cross Y, okay? And it's XY component, or the probability of X comma Y, is just PX FYX, okay? And the output state Q on Y is then given by Q sub Y, the probability of Y, okay? It's the sum over X PX FYX, okay? So this is all standard and it's very well known, okay? But the point is that in classical information theory, we have, using this joint distribution associated with the classical channel and initial state, we can formulate dynamical analogs of these classical information measures, okay? So using this joint state, which I call var theta of P comma F, okay? And this is to emphasize that these dynamical information measures aren't just associated with a channel, but they're associated with a channel together with an input state on that channel. So the input data here is really a channel together with an input state, okay? So this is very important here. And so in such a case, the dynamical joint entropy, which we'll call S of P comma F, is just the Shannon entropy H of this joint distribution. Then the dynamical conditional entropy is the Shannon entropy of the joint distribution, or the dynamical joint entropy, minus the Shannon entropy of the input state P. And the dynamical mutual information, I of P comma F, is just the Shannon entropy of Q minus the Shannon entropy, the conditional entropy H of P comma F, okay? Moreover, there's another very important information measure, or dynamical information measure, called the channel capacity of a classical channel F. And this is given by C of F, where we take the supremum all over all input distributions P of the dynamical mutual information, I of P comma F. Okay, so we then see that the key to defining dynamical measures of classical information is the existence of this canonical joint state var theta P comma F, associated with the channel F and an input state P, okay? And what follows, we will refer to this var theta, this canonical joint state, as the classical state over time associated with P comma F, okay? So as such, given a state rho on a matrix algebra, so going to the quantum picture now, right? If I have a quantum channel E going from, one matrix algebra A to another matrix algebra B, in an initial state rho, we wish to find a sort of joint state, which to distinguish from the classical case, instead of calling it var theta, I'll call it psi of rho comma E in the tensor product A tensor B, which may be viewed as the quantum analog of the classical state over time, var theta P comma F, okay? So to do this, we now introduce a formalism which incorporates both classical channels and quantum channels in a single framework. And this formalism is just what we call the multi-matrix algebra formalism, okay? So I'm sure all of you are familiar with matrix algebras. So moving on to multi-matrix algebras is just a very small step, okay? So just to make sure we're all on the same page with notation, okay, I use M sub n to denote the C-star algebra consisting of n by n matrices, okay? And note that M sub 1 is necessarily then just the complex numbers, okay? So given a finite set X, okay, the C-star algebra, which is the direct sum of M sub Mx, okay, is referred to as a multi-matrix algebra. So multi-matrix algebra is nothing more than just a direct sum of matrix algebras. So an element of a multi-matrix algebra is just you can think of as a vector of matrices. Okay, so it's just a vector of matrices, and the addition and multiplication in this algebra is just then defined component wise. Okay, and the trace of an element A of this multi-matrix algebra is just the sum of the trace of its components. Okay. So like I said, one reason for introducing the multi-matrix algebra formalism is so that we can talk about classical channels and quantum channels on equal footing. Okay, so the first example of a multi-matrix algebra I'll introduce is when these coefficients M sub x here on A are all just 1. Okay, so if m sub x is 1 for all x and big X, okay, then A is just a direct sum of complex numbers. Okay, and the direct sum of complex numbers indexed by x is canonically isomorphic to the algebra C to the x of complex value functions on x, right? Because an element of the direct sum of complex numbers indexed by x is just the choice of a complex number for every x and x. Well, that's the same data as a function. Okay, so in the case when this m sub x is equal to 1, so namely that every matrix algebra factor is just the complex numbers, we'll use the notation C to the x. Okay, and I will refer to this as a classical algebra. Okay, so an element in a classical algebra C to the x, we can then always write it as the sum over x and x of rho x delta x. Okay, where rho x is a complex number and delta x is just a Dirac delta of x, namely the function that takes the value 1 at x and 0 otherwise. In other words, it's just a point mass distribution supported on x. And these Dirac deltas, delta x, form a basis of this complex value functions on x. Okay, so every element rho in this classical algebra, we can write it in such a way. Okay, now notice that for classical algebras, we have that complex value functions on x cross y is canonically isomorphic to Cx tensor Cy. Okay, so this is one way that we can start to unite classical channels, or the concept of a state over time for classical channels with the state over time for quantum channels. Because if you notice, the state over time for classical channels is a distribution on x cross y, right? Whereas in quantum theory, we use tensor products. We don't use Cartesian products. Right. So using this multi-matrix algebra formalism in some sense turns Cartesian products into tensor products. Okay. So now I'll talk about states on multi-matrix algebra. So let X be a finite set and let A be a multi-matrix algebra. So it's just a direct sum of matrix algebras. Okay. So an element A, which has components AX, is said to be self-adjoint if and only if each of its components is self-adjoint. In other words, that AX dagger is equal to AX for all X and X. It's said to be positive if each of its components AX is self-adjoint and has non-negative eigenvalues for all X and X. And an element is said to be a state if and only if it is positive and of unit trace. And so the set of all states on a multi-matrix algebra A, I'm going to denote by this S of A here. So here's an example everyone is familiar with. So if X is just a singleton, right? If X just consists of a single element, okay, then a multi-matrix algebra is just a matrix algebra. And a state on such a matrix algebra is just a positive matrix of unit trace that is a density matrix. And we all know what density matrices are. Okay? At the other extreme, if I have a classical algebra, okay, then a state consists of an element rho, sum of rho x delta x. Okay, and from the definition of state, it must be positive and of unit trace. Okay, and those conditions, when translated into this example, yield that these coefficients rho x must all be non-negative, and they must sum to the identity from the unit trace condition. Okay, so in other words, a state on a classical algebra is nothing more than just a probability distribution on the set which parameterizes, on the underlying finite set X, which we're considering complex value functions on. Okay, so this is why I was referring to probability distributions on finite sets before as states, because in the language of multi-matrix algebras, they literally are states. Okay, so from such a viewpoint, okay, in quantum information theory, right? Essentially, what we study are transformations of quantum states, right? Under what are called completely positive trace preserving maps. Okay? So from our perspective, right, quantum theory, there's no axioms or anything, right? We're just studying quantum states that transform according to CP/TP maps. Okay, and what we do as human beings is sort of try to discern the meaning of what certain transformations of states are. Okay, and I'll say more about why there's no axioms necessary, especially when using multi-matrix algebras. But in any case, so we're going to be working in a mathematical category, Okay, which means we have objects which are going to be states, and they're going to transform to a certain class of maps. And these are going to be called CPTP maps. Okay, so to define CPTP maps, I need to define some properties first. So let's say I have a map E and HOM AB. So when I say HOM AB, that just means linear maps from A to B. So a linear map E from A to B, where A and B are multi-matrix algebras, is said to be dagger preserving if and only if E of A dagger is equal to E of A dagger, okay, for every element A and A. So I think in the quantum information theory literature, it's more common to consider Hermitian preserving maps, but notice that this dagger preserving condition implies Hermitian preserving, right? Because if A is Hermitian, then A dagger is equal to A dagger is equal to A, and then you just get E of A dagger is equal to E of A. Okay. So a map is said to be trace preserving if and only if the trace of E of A is equal to trace of A. It's said to be positive if it preserves positive elements. So namely, if we feed the map a positive element, the output is also a positive element. And it's said to be completely positive, which is a more technical condition that we don't have to worry about, if and only if E tensor the identity on C, which is a map from A tensor C to B tensor C, is positive for every multi-matrix algebra C. Okay. And a map is said to be CPTP if and only if it's completely positive in trace preserving. Okay, so if you're not familiar with CPTP maps, we just think of them as a class of linear maps between multi-matrix algebras that preserve states. So in other words, if you input a state into a CPTP map, it outputs a state. Okay. So are there any questions or anything at this point up to here? Is anything not clear? No? Okay. Okay, so now is where we can formulate classical channels in terms of CPTP maps between multi-matrix algebras. Okay, so let E be a CPTP map between classical algebras. So remember, a classical algebra just consists of complex valued functions on a finite set X. Okay, and since a Dirac delta X is a state, right? Because it's a point mass distribution on X, so it's essentially a probability distribution on X. Then if I feed delta X into a CPTP map E, okay, then the output should be a state as well, right? And since the output channel, the output or the source algebra is also a classical algebra, the output should be a state on C to the Y, which is just a probability distribution of Y. Okay, so for a fixed X, I get a probability distribution on Y, okay, whose value at Y is what I'm going to call EY sub X, okay? So in other words, a CPTP map between classical algebras is equivalent to the data of a stochastic matrix, E sub Y, and is thus equivalent to a classical channel, okay? As such, the elements E sub Y X will be referred to as the conditional probabilities associated with the classical channel, okay? So here's some more examples. So the first example is the one everyone here is familiar with. So it's CPTP map between matrix algebras, or what we'll call a quantum channel. Okay, so a CPTP map where the domain is a matrix algebra and the codomain is a classical algebra, we'll call it POVM. Okay. So does anyone see why a CPTP map from a matrix algebra to a classic algebra is equivalent to a POVM? What would normally be referred to as a POVM? Because I think I can write on this here. Because in such a case, right, we have E of rho is necessarily of the form sum over Y and Y trace of rho dy delta Y. Okay, so it determines a class of positive operators, E sub Y, and the trace preserving condition implies that the sum of these operators should sum to the identity. Okay, so a CPTP map from a matrix algebra to a classical algebra is equivalent to the definition of a POVM. Okay, so instead of stating a POVM as just a collection of operators, we can think of a POVM dynamically, okay, within our category that we're working in. Okay, so if I switch the direction and consider a CPTP map from a classical algebra to a matrix algebra, then this corresponds to a preparation map. So here an input state now is a probability distribution, okay? And then the output of such a channel should be a state or a density matrix on the matrix algebra M sub M, okay? So if I start out with a state Px on C to the X, okay? So then, or I should say E of delta X, right, is going to be some state, let's say rho X on M. And then if I start out with a linear combination of these delta X's corresponding to a more general probability distribution, okay, then I just get a sort of ensemble of states. And if I have a CPTP map from a matrix algebra to a direct sum of matrix algebras, then this corresponds to a quantum instrument, because then this is just equivalent to the data of a collection of completely positive maps indexed by Y, such that when I take the sum of those maps, I get something trace preserving. Okay. So in what follows, what's called the Yamakowski isomorphism will play a fundamental role. Okay, so in quantum information theory, yes?
That is, I think it's missing one example, right? The only one that is missing is when both sides have this direct sum. And there is no concept in quantum theory that has this interpretation.
Yeah, when both sides are a direct sum, I don't know of a standard sort of
Okay.
yeah, formulation of what that means. Okay. I mean, I could say something more about that case, but I won't get into it right now. Okay, so in quantum information theory, we've all heard of the Choi-Yamakowski isomorphism. Okay, so I'm going to make use of what I call the Yamakowski isomorphism, which appeared before the Choi-Yamakowski isomorphism. So this isomorphism first appeared in a paper by Yamakowski in 1972. Okay, and then Choi came out with a variant of the Choi-Yamakowski isomorphism, which physicists found more useful for certain reasons. And so the Yamakowski isomorphism was kind of left behind, and people just kind of worked with the Choi-Yamakowski isomorphism. But for our purposes, we find that the Yamakowski isomorphism is actually more suitable for what we're trying to do. Okay, so given now, when Yamakowski first formulated this isomorphism, it wasn't in terms of multi-matrix algebras. Actually, I don't remember the exact generality in which his paper worked, whether it was matrix algebras or finite dimensional C-star algebras or something like this. So I didn't state this theorem, but every multi-matrix algebra is isomorphic to a finite dimensional C-star algebra. So people who work in C-star algebra cases, if you think of a map, CPTP map between, where you have direct sums on both sides, you can just think of it as a CPTP map between finite dimensional C-star algebras. Okay. But in any case, so the Yamakowski isomorphism is a map J from linear maps from A to B to the tensor product A to B. Okay, and it has this nice formula. J of E is equal to identity on A tensor E of mu A star of 1. Okay, so here mu A star is the Hilbert-Schmidt adjoint of the multiplication map on A tensor A to A. So the multiplication map just takes A tensor B to A times B. Okay, so or the linear extension of that. Right, so this is right. We can write down also what the Hilbert-Schmidt adjoint means in the context of multi-matrix algebra, and it turns out that mu A star, the Hilbert-Schmidt adjoint of the multiplication map, is a map necessarily from A to A tensor A. So the output of mu A star of 1 is an element of A tensor A, and then you leave one factor alone, and then you leave the first factor alone, and then apply E to the second factor, and the result is the Yamakowski state of E, which we often call the channel state of E. Okay, so notice if any of you are familiar with the Choi-Yamakowski isomorphism, the Choi-Yamakowski isomorphism relies on the choice of a basis, so it's sort of basis-dependent construction. So you can see here from the definition of this Yamakowski isomorphism, it's basis-independent. At no point am I choosing a basis anywhere here. So that's one reason we like it. Okay, so now the main reason why we use the Yamakowski isomorphism comes from this classical example. So remember, the motivation for all this is I want to generalize the classical state over time. Okay, so let's go back to the setting of a classical channel E, okay, from CX to CY. and let's say I have a state on Cx, okay? Then the classical state over time is given by the sum over x and y, rho x, EYX, where EYX are the conditional probabilities associated with the classical channel. Okay. And if you write down what the Yamakowski state of E is, okay, then this classical state is actually equal to rho tensor identity times the Yamakowski state of E. Okay. Now notice that the right-hand side here, this rho tensor identity times the Yamakowski state of E, makes sense for any CPTP map between multi-matrix algebras. Okay, so the right-hand side of here, so what I've done here is I've written the classical state over time in such a way that makes sense for any CPTP map between multi-matrix algebras and any. So remember, it's not just a quantity associated with the channel, but also an initial state rho. Okay, and in this case, in the classical case, this adjoint of the multiplication map is the classical cloning or copy map. So mu star of delta x is just the sum over x and x delta x. Okay, so when I write this classical state over time in terms of the Yamakowski state, right? So now it gives me an idea of how to write, what a quantum state over time should be. Okay, so notice that for classical algebras are commutative. Okay, there are many expressions that I can write in rho tensor identity in J of E. Okay, in a non-commutative algebra that would give me rho tensor identity times J of E in a commutative algebra. Right. So for example, I could take 1/2, or I could take any convex combination of rho tensor identity times J of E plus J of E times rho tensor identity, right? In a non-commutative algebra, that would give the same thing here in a commutative algebra. So it's not, immediately clear what we should take as the state over time. There are many different sort of functions of rho tensor identity in the Yamakowski state that would yield the same expression for classical channels. Okay, and so another condition that this classical state over time satisfies that we want from a quantum state over time is that if we trace over y, right, which corresponds to the the codomain of the channel, then I get the input state rho, and if I trace over x, I get the output state E of rho. Okay, so these are conditions that we would want from a quantum state over time, namely that if the commutator of rho tensor identity with the Yamakowski state E is 0, okay, then a quantum state over time psi of rho comma E should reduce to this, what the classical state over time is, namely rho tensor identity times the Yamakowski state of E. Okay, and we would also want this marginal condition as well. Okay, so now I'll come to the definition of quantum state over time. Okay, so given multi-matrix algebras A and B, we let P of AB be states on A cross CPTP maps from A to B, and an element rho comma E in this set P of AB will be referred to as a process. Okay, so for us, the process is not just a channel; it's a channel together with an input state rho, okay? Because it's really the process of taking rho to another E of rho. So a state over time function associates every pair A comma B of multi-matrix algebras with a map psi from P of AB to A tensor B, such that when I trace over B, I get the input state rho, and when I trace over A, I get the output state E of rho. That's going to be our bare bones definition of what a quantum state over time is. Okay, and so now a very important remark is that while the marginals condition in the definition of a state over time function ensures that the state over time is of unit trace, right? If I have a state over time function, then the output psi of rho comma E must be of unit trace, right? Because its marginals are both states, right? And they are both of unit trace by definition, okay? But there's nothing in the definition of a state over time, right, that ensures that the output state, I should say in quotes, state is an actual quantum state. Namely, there's nothing that stipulates that the state over time should be positive, okay? And when you look at this, expression here for the classical state over time, rho tensor identity times J of E, if you plug in, let's say, a quantum state rho and a quantum channel E between matrix algebras, you get something which is not positive in general. Okay, so this was kind of, a clue, a first clue that states over time are not actual quantum states. Okay, they're a sort of generalization of quantum states where you have, bipartite states on a tensor product where the marginals are states, but the matrix itself is not necessarily positive. Okay, so here are some examples of state over time functions. So the map psi of rho comma e equals rho tensor e of rho is what we call the uncorrelated state over time function. It's not a very interesting state over time function, but it satisfies the definition nonetheless. Okay, so if I take a spectral decomposition of rho, okay, where I'm thinking now of rho is a state in a matrix algebra, okay, then the map psi of rho comma e, which is the sum over lambda p lambda e of p lambda, okay, is what we call the Oya or compound state over time function. Okay, so notice that these first two examples, they don't use this Yamakowski channel J of E. Okay, and they don't satisfy this condition because we haven't included this condition here in the state over time. So if we really want to view a state over time as a generalization of the classical case, then it should satisfy this condition when rho tensor identity and the Yamakowski state commute. Okay. So in all the rest of the examples, they do satisfy that condition. Okay. So for example, the map psi of rho comma e equals square root of rho tensor identity times Yamakowski state of e times square root of rho tensor identity is what's called the Leifer-Speckens state over time. This was first introduced by Leifer-Speckens in a long paper on quantum Bayesian inference. Okay. So the map psi of rho comma e equals rho tensor identity times Yamakowski state is what we call the right Bloom. If I switch the order of J of E and rho tensor identity, I get the left Bloom. And I kind of use this special notation, let's say Tau of rho comma E, which is 1/2 times the anti-commutator of rho tensor identity and the Yamakowski state of E. So this we call the symmetric Bloom state over time function. Okay. So notice that while the output of right Bloom and left Bloom is not Hermitian in general, for the symmetric Bloom, the output is Hermitian. Okay, so while it's not positive necessarily, we do get a Hermitian state over time. Okay, and this last example kind of generalizes the left Bloom, right Bloom, and symmetric Bloom, and the Leifer-Speckens state over time. So if I have a finite probability space x comma p, so that just means I have a state on a finite set x, and a function f from x to 0 to 1. Okay, so no conditions on the function other than that. Then psi of rho comma e, which is the convex combination sum over p of x of rho raised to the f of x tensor identity times Yamakowski state of e times rho raised to the 1 minus f of x tensor identity is also a state over time function. Okay, and it does satisfy this condition here with the commutator of rho tensor identity in J of E, which we want if we want to view a state over time, quantum state over time as a generalization of a classical state over time. Okay, so this last state over time that I wrote here, quantum state over time, which contains the symmetric Bloom, right Bloom, and left Bloom, and also the Leifer and Speckens Bloom as special cases. Okay, it's not positive in general. Okay, so initially this was thought to be a defect of states over time, right? And I think one reason why Oya defined his state over time the way he did was he wanted to get something that was positive, something that was an actual quantum state. So while we thought the negativity of these states over time was a deficiency at first, it was pointed out by Fitzsimons, Jones, and Vidral in a paper from around 2015 that the negative eigenvalues of a state over time are actually a witness to temporal or causal correlations that exist throughout the dynamical evolution of the state rho as it evolves according to a quantum channel E. Okay, so whereas a usual quantum state, right, is something that encodes spatial correlations, right? So if you have an entangled state on A tensor B, it's encoding spatial correlations between, let's say, two particles, one on A and one on B, whereas state over time is a generalization which can encode not only spatial correlations, but also temporal and causal correlations as well. Okay, so given all these examples of state over time functions, how do we determine which one is correct or the most physically meaningful? Okay, so for this, we kind of take the axiomatic approach and define some properties that states over time may or may not satisfy, and distinguish the different approaches by the properties they satisfy, rather than just looking at their formulas. Okay, because it's not really the formulas that are important, right? Anytime anyone gives a formula for anything, right, there's, a formula is never unique. So what's more important is the properties that something satisfies. Okay. So a state over time function is said to be positive if the output psi of rho comma e is positive for all processes, rho comma e. It's said to be Hermitian if the output psi of rho comma e is self-adjoint for all processes. It's said to be state linear if it's linear in the state argument, channel linear if it's linear in the channel argument, and classically reducible, or a classical generalization in some sense, if when the commutator of the Yamakowski state of E with rho tensor identity is 0, okay, then we get the formula for the classical state over time, rho tensor identity times J of E. Okay, so yeah, I put a table here, but it's kind of hard to read. So the right bloom, so all the blooms, right bloom, left bloom, and symmetric bloom are all state linear, channel linear, classically reducible. The symmetric bloom is also Hermitian, whereas the Leifer-Specken state over time, the one with the square root, is Hermitian, channel linear, and classically reducible, but it's not state linear. It's not linear in the state. Okay. But the classical state over time is linear in the state. Okay. So if we want to view states over time, quantum states over time, as a generalization of the classical case, then they should be linear in the state as well. Okay. So the classical state over time satisfies state linearity, channel linearity, and the fact that it's given by this formula. Okay. So if we want to view a state over time function psi as a direct generalization of the classical state over time function bar theta, then psi should be Hermitian, state linear, channel linear, and classically reducible. Okay. So at present, the only known state over time function which satisfies all of these properties is the symmetric bloom. And we think we have a proof that the symmetric bloom is in fact characterized by these properties, but it's quite a long and technical proof, and we're still not 100% sure yet. Okay, so now that we've defined quantum state over time, quantum states over time, and sort of my favorite example, symmetric bloom. Okay, I can go back to this original problem that I was talking about at the beginning of the talk, namely, how do we formulate dynamical measures of quantum information? Right? So if I have a quantum channel, the data of a quantum channel in an input state rho, right? Now I can mimic what we did in the classical case when we had the classical state over time to define dynamical measures of quantum information. Okay, so this corresponds to kind of solving two problems. The first problem is to come up with a state over time, but since we realized that states over time are not in general positive, I can't just use von Neumann entropy to evaluate at a state over time. I have to use some generalization of von Neumann entropy to Hermitian matrices. Okay, and so for this we use this functional. Okay, so the entropy of a process rho comma e with respect to a state over time function psi. Okay, so I don't want to be sort of biased in any way towards a particular state over time function. So I'll define the entropy with respect to the choice of a Hermitian state over time function. Hermitian, I'll recall, just means that the output state over time is always self-adjoint. Okay, so we define the entropy of a process rho comma e with respect to psi as minus trace of psi rho comma e log of magnitude of psi of rho comma e. Okay, so since psi of rho comma e is Hermitian, right, it's diagonalizable, right? So its eigenvalues form what's called the quasi-probability distribution. And so what we're doing is we're plugging in the absolute value of the eigenvalues into the log, but we're not taking the absolute value of the eigenvalues outside the log here. Okay. Now, there have been other approaches to defining, generalizing von Neumann entropy to Hermitian matrices. So there's a paper that came out recently where they put the absolute value on the psi of rho comma e as well. Okay, but we found that that's not the most natural from the perspective of generalizing the classical case. And the reason why is when we don't put the absolute value here on this side, we get the following theorem. So if I have a unitary process, so my channel is of the form add u, meaning given an input state rho, the output is u rho u dagger. Okay, then if psi is the symmetric bloom, right, left bloom, or the Lee for Speckens bloom, okay, then we get that the associated entropy of rho with respect to a unitary channel is just the von Neumann entropy of rho. Okay, and this is a property that we definitely want, because in the classical case, you also get an analogous property. So let me see, this was all the way back. So dynamical measures of classical information. So if F is a completely deterministic classical channel, so let's say F, for example, is the identity map, then S of P comma F is just equal to the Shannon entropy of P. Okay, when F is, let's say, a deterministic map, completely deterministic. Deterministic. So in other words, just a function. Okay. So if you were to use a different definition where you use the absolute value or magnitude on inside or outside the log as well, okay, then we wouldn't get this theorem here. Okay, so in particular, S of psi of rho comma identity is just the von Neumann entropy of rho. So now we can define, the dynamical analogs of conditional entropy and mutual information. So the conditional entropy of a process, rho comma E, with respect to psi, okay, is just the entropy of the process, rho comma E, minus the von Neumann entropy of rho. And the mutual information is just the von Neumann entropy of rho plus the von Neumann entropy of E of rho minus the entropy of the process, S sub psi of rho comma E. So I also defined information discrepancy, but I'm not going to talk about that information measure for the sake of time. Okay, and while the entropy, conditional entropy, and dynamical mutual, the conditional entropy and the entropy, these dynamical information measures can be negative, we find in all examples that the mutual information is non-negative. So we don't understand why yet, and we don't have a proof, but we've checked it with millions of examples on the computer, and we've yet to find a case where the mutual information is non-negative. So what is this telling us about quantum processes? So we don't really have an operational interpretation of these information measures as of yet, but in some cases we do. Okay, so let's consider a measurement map. Okay, so a POVM, so namely just a CPTP map from a matrix algebra to a classical algebra. Okay, so again, this means that there's positive elements, E sub y, that sum to the identity, such that E of rho is sum over y, trace of rho EY delta y. Okay, so a measurement process, rho comma E, where E is a POVM with rho pure. Okay, so this is a sort of technical condition that we needed for the proof of the next theorem. It's said to be non-disturbing if and only if the image of rho, when rho is viewed as an operator on the associated Hilbert space, which in this case, since rho is pure, is just going to be a one-dimensional subspace of the Hilbert space. It's said to be non-disturbing if and only if the image of rho is invariant with respect to the POVM elements EY associated with the CPTP map E. Okay, that just means if I take E sub y as an operator and apply it to rho or any other, any scalar multiple of rho, it just stays in that subspace image of rho. Okay. Otherwise, if a POV element, takes an element of an image of rho and when applying E sub y, the output is no longer an image of rho, then we say that the measurement is disturbing. Okay. This is in my paper, we showed that this definition is equivalent to other notions of disturbing and non-disturbing measurements in the literature. Okay. So we then have this theorem. So if rho comma E is a measurement process with rho pure, and psi is the symmetric Bloom state over time function, then the following statements hold. So if rho comma E is non-disturbing, then the mutual information associated with the symmetric Bloom of rho comma E is 0. And if rho comma E is disturbing, then this mutual information is in fact positive. Okay, so in light of this theorem, the mutual information of a measurement process with respect to the symmetric Bloom, sort of quantifies the amount of disturbance of a quantum measurement. Okay, it gives a precise number associated with the disturbance. Okay. And the symmetric bloom is kind of special in this case. So for example, if we use a different permission state over time function, such as the Leifer-Speckens state over time function, they don't sense any disturbance in the measurement. So for example, when you evaluate the mutual information associated with the Leifer-Speckens state over time function, you get 0. Okay, whether or not the measurement is disturbing or non-disturbing. Okay, so next I will talk about one application of states over time. So the first was to kind of solve this question about dynamical information measures. Okay, and in doing so, we kind of stumbled upon this other application, which was to give a sort of a quantum formulation of the classical Bayes rule, right? So now that we have a mathematical formalism to talk about classical probability theory or classical information theory and quantum information theory at the same time, right? Once we write the classical Bayes rule using the formalism, right, of multi-matrix algebras, we can write what that means and interpret it for a general quantum process. Okay, so if we take classical random variables x and y, okay, then Bayes' rule states that the probability of y given x times p of x is equal to the probability of x given y times p of y. Okay, so from a dynamical perspective, okay, let's say p of y given x are the conditional probabilities associated with the classical channel E between classical algebras. Okay, and rho x corresponds to the components of a classical state on C of x, and py corresponds to the components of a classical state on cy. Okay, then the left-hand side of the classical Bayes rule is just the classical state over time, var theta of rho comma e. Okay, and the right-hand side, okay, is just the classical state over time of a channel going in the opposite direction, where the associated conditional probabilities are p of x given y instead of p of y given x. Okay, but to get an equality here, see the classical state over time on a channel going in the reverse direction, right, is an element of c of y tensor c of x, not c of x tensor c of y. Okay, so to get an actual equation in the multi-matrix algebra setup, we need to use the swap isomorphism, which is the lexicographic swap, which maps elements on c of y tensor cx to c of x tensor cy. Okay, so here we can literally rewrite the classical Bayes rule here in the multi-matrix algebra formula as the classical state over time associated with rho and e is equal to the swap of the classical state over time of the state E of rho and a channel going in the opposite direction. Okay, so this is how we'll write, so it's a sort of dynamical formulation of Bayes rule that also will make sense for any quantum process as well. Okay, so let's say I have a pair A comma B of multi-matrix algebras, and I have a quantum process, rho comma E, and a state over time function psi. Then a process sigma comma E bar, okay, where E bar is a map going from B to A, is said to be a Bayesian inverse of rho comma E, if and only if the state over time psi of rho comma E is equal to the swap of psi of sigma comma E bar. Okay, so this we'll refer to as the quantum Bayes rule associated with the state over time function psi. Okay, so in such a case, E bar is said to be the Bayes map associated with the quantum Bayes rule. Okay, so notice that this gives us a quantum Bayes rule for every choice of a state over time function, right? You can formulate this equation here with respect to any state over time function psi. And so what we see is that you can view this as an equation where you're kind of solving for the map in the opposite direction. So you start out with rho comma E, and sigma by the marginals condition on the definition for states over time is necessarily E of rho. Okay, so a Bayesian inverse is essentially a map in the other direction that satisfies the equation. Okay, and so here's a sort of like cartoon of what's going on here with slightly different notation. So here we have a quantum process E in rho corresponding to Alice sending a state rho to Bob through a quantum channel E. And then we have a sort of reverse process of Bob sending the state E of rho to Alice through a channel going in the opposite direction. So here we have the state over time. So I was calling it psi of rho comma E in this talk. So in this picture, it's called E star rho. And then we have the state over time associated with this process, And these two states over time are related by the swap isomorphism, with the lexicographic swap isomorphism, which we're calling tau in this case. Okay, so there's some famous examples which yield, well, I should say there are some, straightforward examples which yield, famous maps in quantum information theory. So in particular, if psi is the Leifer-Specken state over time function and ARB are matrix algebras, then Bayesian inverses always exist. I think they're unique, I'm not sure. And the Bayes map going in the other direction with respect to this Bayes rule here, so namely a map that satisfies this equation, is the Petz recovery map. Okay, so the Petz recovery map is a famous map, quantum information theory. Okay. So also if I take the Leifer-Specken state over time function, and I start with a measurement map, so a POVM from a matrix algebra to a classical algebra, okay, then a Bayesian inverse of a POVM is precisely a preparation of a state. Okay, so a lot of times you'll hear in the literature how preparations and measurements are kind of like dual processes of each other. So this is a precise mathematical statement. It says that a preparation is a Bayesian inverse of a measurement and vice versa.
So what is Petz recovery map?
Yeah, so I was going to include it in the slides, but I was kind of running out of space. I don't remember the formula right offhand. I have an idea of what it is. So you sandwich, so E bar from B to A. So you start out with sigma, and yeah, I forget the formula offhand. Yeah.
So why this Leifer-Specken state is special and why looks like the square root of O tensor I?
Yeah, so there's these different examples of states over time, right? And there was this kind of question of like, what's the best one, right? Or what's the most natural one? And we found it depends on what you're trying to do. So for quantum Bayesian inference, it seems like this Leifer-Specken state over time with the square root of rho seems to be the most natural. For information measures, for defining dynamical information measures and entropy and things like this, it seems like the symmetric Bloom is the more natural one. And whereas the Petz recovery map always exists, so you always have Bayesian inverses with respect to the Leifer-Specken state over time function. With the symmetric Bloom, you often don't have Bayesian inverses. So there's often no map going in the opposite direction, CPTP map, satisfying the Bayes rule. Okay. So I don't remember the formula for the Petz recovery map, but for those of you who are familiar with it, the Bayesian inverse or the Bayes map going in the opposite direction with respect to the Leifer-Specken state over time function is the Petz recovery map. So from the point of view of the quantum Bayes rule, the Leifer-Specken state over time function is sort of like the most natural one. Okay, so we also have a quantum entropic Bayes rule, which combines, Bayesian inference together with the, entropic formulation of dynamical information measures. So the classical entropic Bayes rule. So if I have a pair of random variables x, comma y, then the entropic Bayes rule is that h of y given x plus h of x is equal to h of x given y plus h of y, where h is the Shannon entropy. And h of y given x is the conditional entropy. Okay. So we have a quantum entropic Bayes rule that we proved. So the statement is that if psi is a Hermitian state over time function and sigma comma e bar is a Bayesian inverse of rho comma e, then the conditional entropy of rho comma e plus the von Neumann entropy of rho is equal to the conditional entropy of sigma comma e bar plus the von Neumann entropy of sigma. Okay. So in particular, if psi is the Leifer-Specken state over time function, then for every process rho comma e, there exists a Bayes map such that the above equation holds. Okay, so this is a sort of synthesis of what we were doing with dynamical information measures and quantum Bayesian inversion as well. Okay, so much for my sort of last slide here, as I was saying, there's this question of which state over time, quantum state over time, is the most natural. Yeah, I think I have one more slide after this. And what we're starting to, a viewpoint that's starting to emerge is that the symmetric Bloom state over time function tells us something about the causality of a quantum channel. Okay, so or the reversibility of a quantum process. So as I was saying before, if I have a quantum process rho comma e, right, then if we use the Bayes rule with respect to the symmetric Bloom state over time function, okay, this Bayes rule here, there's usually not a map E bar going in the opposite direction that satisfies this quantum Bayes rule. Okay, so when there is not a map going in the opposite direction that satisfies this equation, okay, then we say that a process is strictly causal. Okay, so it really tells us that, you know, in quantum theory, for example, let's say a unitary process works just as well in the forward direction as it does the backwards direction, right? So when we have a process that there is no Bayesian inverse, then we say that this is strictly causal. So it seems the symmetric Bloom state over time function is telling us something about the degree to which the input state rho causes the output state E of rho, right? So for example, if you have a very noisy channel, right? Or let's say your channel is no matter the input state, just takes, a fixed output state, right? Then you wouldn't really say in this case that the output state was caused by the input state rho. Okay, so the symmetric Bloom we see as giving a measure of sort of causality, or saying something about the degree to which the output of a channel is caused by the input of a channel. Okay, and for my last slide, I just sort of give the big picture with what we're trying to do with states over time. So in this talk, I just talked about processes that involve a single step of time. So you have algebras A and B, which exist at two instances of time, say time t equals 0 and t equals 1. Okay, but more generally, we're interested in multi-time processes, and not only this, but processes of sort of quantum states corresponding to spatial regions involving in time. Okay, so the slogan I kind of like to say is that in relativity theory, right, space and the fields on it, evolve over time into a single entity, which we call space-time. In quantum theory, we have states evolving over time, but the theory makes no reference to a single entity which globally encapsulates the evolution of a quantum state over time. In other words, quantum theory lacks an intrinsic analog of space-time, right? So for example, space plus time in classical physics equals space-time, but what is state plus time? Equal, okay? And what we're trying to do with this quantum states over time stuff, which is just very new, we only started working on this a couple of years ago, is sort of, give a sort of analog to space-time in quantum theory. And hopefully, perhaps the lack of such a, of such an analogy in quantum theory has to do with the fact that, of the problems of formulating a quantum theory of gravity, right? Because part of the problem is that, in relativity theory, the mathematical apparatus that we use is so different from the mathematical apparatus that we use in quantum theory. Okay? So kind of taking this sort of it from bit perspective, that at the fundamental of reality, we have, information. Okay? So we have sort of information propagating in time, right? Then perhaps once we have, an appropriate notion of a general state over time for information propagating in time, then perhaps we can extract space-time from such a construction. Okay, I'll stop here.
In the beginning of the presentation, we were talking about the classical case, and you could define the channel capacity, right?
Yeah.
Using the information. And what about using this format?
Yeah, so I've defined it to use a channel capacity, but I haven't really looked into it much yet, and I don't know how it's related to other capacities in the literature. But that's another reason why I wanted to mention, we have this conjecture about whether this dynamical mutual information is positive, right? We found in all cases it's positive, right? If it was negative, right, then it wouldn't really make sense to say that the capacity of the channel is negative, right? So it seems like if it is in fact positive or non-negative, right, then it would give a natural measure of channel capacity. So you fix a channel, right, and then you take the dynamical mutual information over all input states rho, and you take the supremum of that, right, then this would define a natural channel capacity associated with the channel.
Also regarding the motor information, when you write the large classes of examples, you mean like for the function over time that you example of functions over time showed us, for all of them is always non-negative?
No, no. When I say for large class examples, I mean like unitary evolution, partial trace, things like this. But when we say that it's non-negative for a large class of examples, we mean that, yeah, for all the states over time functions we've ever considered, for any sort of example we've ever computed this mutual information with, and we've checked, you know, millions of examples with computers and stuff as well, we always find that it's non-negative.
You also try to think something about the strong subadditivity of the entropy or not yet?
So yeah, so this would be just sub-additivity. So we have this,
This would be subadditive, but what about the strong?
yeah, we don't know about strong additivity.
Even
Right, so we have this entropy functional. So here I'm plugging in a quantum state over time, but it's defined for any Hermitian matrix. And then so in our paper, we have, you know, a list of properties that this functional satisfies, you know, minus trace of A log, you know, magnitude of A. And you know, subadditivity was one of the things we were trying to prove. In fact, for general, one interesting thing for general Hermitian matrices, subadditivity fails. But for some reason, when we plug in states over time, it seems to always be positive or non-negative.
have you found some sufficient conditions or?
Yeah, we don't know. I mean, for general Hermitian matrices, we don't even know sufficient conditions. And so we haven't even, I mean, since we couldn't get past subadditivity, we were looking at, you know, strong subadditivity. Yeah. So there's a paper that came out recently where instead of using minus trace A log magnitude of A, they use minus trace magnitude of A log magnitude of A. And they have some results there about, I think, weak subadditivity, what they call weak subadditivity or something like this. But this seems to be a difficult problem.
Thanks.
So like in that, like identifying whether a channel is causal or not, you mentioned symmetric bloom is the best,
Seems to be.
but so this should be a property of the channel itself, right? So it
No, it's probably the channel plus the state you're inputting the channel.
Okay, and
Yeah.
if you want to make a statement that for any state, it doesn't, it's causal for,
Not for any state. So given a fixed channel, some states may be strictly causal when you put them, and other states may not be. It really depends on the input state.
okay, and just to clarify, this like term causal is inspired by like Preskill definition of causal, like,
I'm not familiar with Preskill definition. So there's another approach to states over time called the pseudo density matrix formalism. Kind of like Vlatko-Bedrol's school. And so they define these pseudo density matrices in a very different way than we define like the right bloom and symmetric bloom. And we're pretty much 99% sure that the symmetric bloom is the pseudo density matrices defined by Vlatko school. I mean, there's some theorems in their papers, but I don't really understand some of the claims because I've asked them. The pseudo density matrix formalism uses these what they call expectation values over time. And whenever I've asked for a mathematical definition of the expectation values over time, they tell me that they don't really have a precise mathematical definition. They're just operationally defined. But if they're just operationally defined, then how can you have a mathematical theorem about it? So I'm not really sure, but it seems to be the case that the pseudo density matrix formalism is the symmetric bloom. And there's a recent paper by no, I don't think Bedrol is on the paper, but other people working on the pseudo density matrix stuff, where they've been really looking at this causality. What does it mean for, you know, a state at one time to be, you know, true cause of a state at a later time? And there's a couple other papers that came out really recently, just in the past few weeks or something, that kind of beat me to this causal formulation definition. But it seems equivalent to what I'm trying to do with the symmetric bloom. But it really depends. Kind of everything we do is not really just a measure of a channel. So there was this notion of channel capacity, which really is just a measure associated with the channel. But everything we're doing is sort of associated with a channel together with an input state. So it's always with respect or relative to an input state.
And also like, in the formalism of quantum form models, matrix, there is something called link product, right? So,
I'm not familiar. A link product?
yeah, so like, basically suppose like, you want to, define a multi-time process.
Mhm.
And there are like elementary quantum operation like state preparation, evolution and measurement,
Right, right.
right? And then how do you suppose you have a process like there is state preparation and at some other time step there is some channel you're applying.
Yeah.
So as a temporal description, how do you define the consolidated entity? So
Yeah, that's a good question. So in our paper, from time reversal symmetry to quantum Bayes rules, we consider exactly this case. We have, because now we can consider everything, we can formulate everything in terms of CPTP maps. So a preparation CPTP map, then we have a channel, which is a CPTP map, and then also a measurement. So we consider what are called prepare, evolve, measure scenarios. And when you look at the composition, right, the first algebra is a classical algebra because it's a preparation, right, which goes from a classical algebra to a matrix algebra. Then we have a quantum channel between matrix algebras, and then a measurement which goes down to a classical algebra. So when you compose these three maps, you get a map from a classical algebra to a classical algebra, and you get a classical channel. And so with this preparation, evolve, measure scenario, we get these classical dynamics corresponding to a classical channel. So you can ask, given the output state, right? What's the probability given the output state that the input state was this? And that's what the classical probabilities mean in that case. I don't know if this answers your question, but we have been looking at these prepare, evolve, measure scenarios, and they just fit right into this, formalism with the CPTP maps.
Okay, please go to the second last slide. The strictly.
The causal.
So, how is unitary process related to this concept?
Yeah, that's a good question. So I think all unitary processes are reversible. So we wouldn't consider them strictly causal, no matter the input state. Yeah, so if you speak to non-quantum information theory people, right, then they only kind of consider unitary transformations. But from kind of a quantum information theory perspective, the unitary transformations are the most uninteresting ones, right? Yeah.
If no, let's step out speaker again.
Well, I don't know if there was any questions from anyone in the audience. Were there any questions from anyone in the audience?
I think it was one in the beginning.
Okay.
There was one in the beginning.
Yes, you asked about the audio.
Oh, okay.
Yeah, if no, we can stop here.
Okay.